In the last video we had a look at photons and how we could calculate how much energy they have, and that was an example of us treating light as a particle. And what we're going to talk about now is the de Broglie wavelength, which lets us carry on a little bit further this idea of being able to cross over particle behaviour and wave behaviour. So in treating light as photons, we are acknowledging that light and all other forms of electromagnetic radiation can behave like both waves and particles. And normally it's just one set of those properties that is more prevalent depending on the situation. Generally speaking, the longer the wavelength, the more wave-like, and so that means that radio waves, for instance, which have the longest wavelength, are the most wave-like of the electromagnetic waves, and the shorter the wavelength, the more particle-like, so gamma radiation therefore is the most particle-like. And visible light is right in the middle of the spectrum, so it's actually the most likely to be able to flip between its properties, so we can see it acting wave-like or particle-like. So we've already got this idea of wave-particle duality, of light waves being able to act as waves when it suits and as particles when it suits. But the thing is, this all goes a little bit further than that. It's not just electromagnetic waves. It's not just light that can behave as a wave or as a particle. In fact, anything can. So in 1923, de Broglie proposed that particles could act as waves. So electrons, protons, and even atoms could act like waves. And he came up with the idea that they would have a wavelength that would depend on their momentum. So the de Broglie wavelength would be equal to Planck's constant divided by the momentum of the object. So remembering that momentum is mass times velocity, that gives us that the de Broglie wavelength would be equal to Planck's constant over mv. So what that means is that if I've got a particle, I can change its wavelength by changing the velocity at which it is moving. Now, obviously, de Broglie didn't just pull this out of the air. He had evidence. And the evidence he had came from this experiment. So what this is basically just an electron gun. So over here, we've got basically a filament, almost like what you find in a filament bulb. It gets really, really hot. Once it gets hot, it gives energy to the electrons so that the electrons can be released. We then put a very high voltage over here so that we can attract the electrons through. So the electrons that have been released from the metal are accelerated through this anode until they hit a sheet of graphite. So a very thin sheet of graphite and just a couple of atoms thick. And then what we see on the other side is that we get rings. So the electrons aren't just going straight through and hitting at a single point. They're creating this broad ring-like pattern. So this is done in a vacuum, so there's nothing else going on. All that's happening is that the electrons are passing through a solid material, and on the opposite side they are creating a diffraction pattern. Now, if you remember, I said diffraction is something that only waves can do. So the fact that these electrons are being diffracted is evidence that the electrons are acting like waves. They must be getting diffracted by the atomic spacing between the graphite atoms. And in fact, if you do the same thing with X-rays, you get a very similar pattern. So we can see X-rays and electrons behaving very similarly when they pass through this graphite, forming very similar patterns. Okay? So the fact that the electrons form a diffraction pattern is evidence that electrons have wave-like properties. And we can even change the size of the circles that are produced by changing the speed at which we send those electrons. So if I change the potential difference, I can change the velocity at which the electrons go, and I can make the pattern bigger or smaller because I'm changing the wavelength. So I'm either getting it closer to the spacing between the atoms or further away, and that will affect how much diffraction we see. So this electron diffraction is actually really useful because it has allowed us to look at smaller things. And obviously when we are using microscopes, for instance, to have a look at small objects, we're limited by how small the wavelength of light is, because it has to match the thing that we're looking at. With the electrons, I can change the speed at which they're going, so I can change their wavelength, so I can find out information about various sized objects and quite small ones as well. Now, if you have a look, these are two examples of things that have been found from electron diffraction. So we've been able to look at the arrangement of atoms inside of alloys. So this is titanium and nickel. So you can see that we've got the larger atoms interspersed with the smaller ones in between, and we can see that there's this really structured pattern here. Other thing we've been able to do is look at the structure of things like DNA as well. So the electron diffraction is evidence of electrons acting as waves, but it is also a very useful tool that helps us probe and find more information about matter as well. Okay, so that's all we're going to talk about for this video. Remember, if you have any questions, just ask when you see me.